Everybody, welcome back. Thrasher here. In this video, we are actually diving a bit deeper into one particular force, a force that we introduced in a prior video. It's the force of friction. There's some nuances. There's actually also an equation that goes along with it. So we're learning and we're getting a deeper understanding of this force due to friction, okay? The definition for friction has kind of two main points. First, friction is a force between two surfaces. It's when one thing is moving and usually sliding against another thing. Those could be two hands, or it could be a couch on the carpet, but it's between two things that are moving against each other, okay? Now, friction also acts in the direction that is opposite of sliding motion. So when you have your hands together, and let's say my hand right here is sliding upward, it's feeling a frictional force that's acting in the opposite direction, downward. Okay, that's a big thing about friction. Friction basically is never helping us. It is opposing how two things are sliding, or sometimes things aren't actually sliding, but they're trying to slide. Friction might be the thing that prevents that sliding from happening. When you have like a couch sitting on a rug, if the couch is heavy, if the rug is really thick, you actually might not be able to move the couch because friction is holding it in place. But it's still true that that frictional force is opposing that attempt at sliding motion. Now, we know that scientists are lazy, and we are going to see an equation for friction. So friction is a force, and we use the letter F for force. How do we signify that it's a frictional force? To be honest, there's a couple different ways. F, again, is used for force. You might see F within a small little f. That's known as a subscript when you have a letter right below. This represents the force. In which force? The force of friction. Another way to write it, and I admit this is how I write it in class, instead of doing FF, because I'm a little lazy, I'll do kind of an italicized, kind of a fancy F. Yeah, it represents force, but because I wrote it like this, it's a particular force. It's the force of friction, okay? And again, it opposes how things are sliding. So here I have someone trying to move this refrigerator. Let's say they're pushing the refrigerator to the right. Friction, here they're using this symbol, it's opposing. So if we're pushing to the right, the frictional force is acting to the left. Maybe a good way to think about friction is what happens when there isn't any friction. And I'm sure you've seen YouTube videos of cars or people sliding on icy roads. Friction a lot of times provides grip. And so if you're lacking friction, you're going to lack that thing that might oppose things sliding, in which case you might have people, or man, in this dangerous situation, a car sliding across, okay? What is causing friction? For our class, we're going to focus on the idea that friction is caused by the roughness of surfaces, okay? When you zoom into material, all material has little ridges and grooves, like little hills and valleys. An example is take like your knuckles. And if you take the knuckles on your two hands, if you kind of put your fists together and you kind of slide them across, you can kind of feel how like the knuckles hit each other, and then maybe they kind of roll over and then they start moving, but then, oh gosh, they hit another knuckle. This is a good model of how all materials, because no material is perfectly smooth, they have these ridges, these hills and valleys. I have a picture right here. What material is this picture? What's your guess? This is actually a zoom in on glass, like glass from a window. What people often think is very smooth. If you zoom in, even glass has these bumps and these ridges, things that can grind and catch against other material, which could cause this thing we call friction. To be honest, that's basically as far as we're going to get into the definition or the cause of friction. Now, there are some smaller scale details. It has to do with like chemical bonding and things like that. Stuff that, to be honest, we're not really going to get into, but there is in fact still modern physics research going into the fundamental cause of friction. So we're going to stick with this first bullet point for our definition. It is an interesting and still ongoing topic. Let's talk about some examples of friction. Man, again, take your two hands together, move them back and forth. You probably feel friction, the resistance, and friction can also be used to generate heat. So when things are rubbing against each other, they can create heat. You are sitting maybe in a chair. A major reason why you're not bloop, just sliding off your chair is there is friction. Friction between your bottom and the top of the chair that you're sitting on. So there's friction right here that's preventing you from just sliding right off. walking is actually a good way to think about friction. The reason why you are able to move forward is your shoes grip the ground, and that actually causes you to be propelled forward. Think about the opposite example, like you're wearing roller skates or you're going ice skating. If you're wearing ice skates, it's kind of easy to kind of move in place and not propel yourself forward. But when you're wearing shoes with rubber soles that has a lot of grip, it grabs the ground and that grip causes you to move forward. Friction is also important because friction is what keeps your socks on. If you didn't have any friction between the socks and your leg, boop, the socks would just slide right off. So a lot of people think of friction as a negative thing, and it often does get in our way, but also friction is vital for a lot of things that we experience. When it comes to cars, if there was no friction, it would be almost impossible for you to grip the steering wheel and then say turn the wheel. In fact, the tires likewise have to grip the ground, just like your shoes grip the ground. The rubber tires have to grip and use friction to pull the car forward. Also, you need friction because that's how you stop your car. Behind the tire, you can't see it in this picture, but behind the tire there are brakes, disc brakes, and you use this clamping mechanism in order to apply friction to slow the car down. We're actually going to show this a little more in detail, okay? So this right here in this GIF, that's what this part is right here. Again, it's kind of behind the wheel. They don't have the wheel in this picture. Here's the brake pedal. This is a simplified diagram. So you press on the brake pedal, it actually applies a force on this piston, which we won't really get into, but it helps apply a lot of force, and it causes these brake pads to squeeze against the disc brake. I'm going to go to another image right here. Okay, here we see in a little more detail, a little more zoomed in, how these brake pads, that's what this is and what this is. When you press on the brake, pressure is applied through this hose, and these brake pads squeeze and apply friction. I don't have a picture of a bicycle, but if you've ridden a bike, you might know that the brakes on a bike, they kind of squeeze against the tire, very similar. So your car relies on friction both to move, the tires grip the ground, but also to stop. The brake pads grip the wheels, and without friction, neither of those things would work. Cars would not work as we know them without the force of friction. Let's do a little more in terms of the microscopic look, because friction also relates to some other phenomena that we see in nature, okay? Again, there's some more technical, some more chemistry-based kind of causes for friction that we're not really going to focus on. It has to do with some chemical bonds that are going on when two materials are close by. Now, as you could tell by just rubbing your hands together, this friction often causes heat. And if friction is strong enough or intense enough and prolonged enough, this rubbing back and forth, this interaction between two surfaces can actually remove, it can tear away atoms and molecules from objects. This is, while given a different name, very similar to the idea of erosion, like when water erodes a cliffside, or when wind maybe weathers a rock formation. It's very similar. When you have material glancing and hitting, maybe rubbing and sliding against one another, there is friction between those materials, and that can cause things to be removed, the atoms and the molecules, the particles to be removed. We call that, in terms of weather in the environment, either erosion or weathering. Sandpaper is based entirely on this idea of friction. The two surfaces move across each other, heat is created, and if you do this long enough, you can actually tear away particles of, say, wood in this case. I actually have an example I want to show you real quick. This is a good simulation from the website PhET. They're a great physics animation site. It is showing two textbooks. So first look at the bottom. I have two textbooks right here. And what I'm going to do with my mouse is I can click and I can drag this chemistry textbook back and forth. And that's what you're seeing up here. This is a zoom in. We're zooming in on kind of the interface right where the chemistry textbook is meeting the physics textbook. And these are representing maybe like the atoms or the molecules, the particles that make up the two books. Again, think, when you rub your hands together, that's friction, and you feel your hands getting warm. We're going to see the temperature of the books increase by this thermometer. Ready? I'm going to move the textbook back and forth. I'm going to first have them pressed together. Okay, they're on top of each other. move them back and forth. That causes heating, makes the particles actually vibrate faster. Notice you see the temperature go up on that right side, just like when you move your hands back and forth. But I'm going to keep going, and I'm going to move it back and forth even more so it's more vigorous. You're going to see when there's a lot of friction, think of sandpaper. When there's a lot of friction, we can actually tear away these atoms and molecules. That's what you're seeing there. We lost material. Things got torn away because of this interaction, because of this friction. So again, sandpaper is a good example, but also when we think of things like rivers eroding the ground, when air erodes materials like cliffs and big rock formation, that is also fundamentally based on the same interaction, okay? Just about done. Thank you for staying with me. I know this might be a slightly longer than average video. So here's our definition again, friction based on sliding objects. It's when two objects are moving against each other. There's an equation for friction. This is how we're ending, going over the equation. It's not too difficult from a math perspective, but man, there is a symbol or maybe a couple of symbols that we haven't seen before, okay? Friction is this symbol F. Remember how I said I like to use kind of like this fancy italicized F? This is representing the force of friction. How strong friction is, how much it opposes that motion. It's based on two things. I'm going to start with this thing right here, this uppercase letter N. That's the normal force. Do you remember? We talked about the normal force, also called the support force. You are sitting in your chair and the chair is supporting you. How much the chair is supporting you is called the support force or the normal force. When we had those two textbooks, they are being supported. So how much friction there is, it is partially based on how much support force there is. And then last one, team, oh man, this is a weird symbol. This is not even an English symbol. This is a Greek letter. This is lowercase Greek letter mu. That's how you pronounce this, M-U, mu. This has a long and technical name. It's called the coefficient of friction, okay? On the bright side, as I'm going to show you in a second, it's just a decimal. It's just a number you're going to be given. Here I have a silly little comic strip, the way you pronounce this symbol, and it kind of looks like the letter U with an extra little tail in the front, but some cats, it's not meow, but some cats make the sound of mew. That's how you pronounce this symbol. Again, I like to draw it with a U with kind of a little extra thing on the front, okay? Let's learn about what this mu symbol is, okay? Mu is a decimal, and the way to think about it is it represents how grippy two materials are. Of course, there's all different materials from concrete and ice and water and wood. Based on the combinations, you might have a different amount of grippiness. Again, it's a decimal. If the decimal is bigger, it simply means more grippy. And it depends on the surfaces. On the bright side, team, there's nothing for you to memorize. This would have to be given to you. A classic way, especially in like old school physics textbooks, is they have these big data tables. This is showing you the approximate values of this symbol right here based on different material. For example, your shoes have rubber soles. They are pretty grippy on concrete. So this 0.68, that's how grippy the material is. That's pretty good. You don't really slip on concrete when you have good rubber shoes on. If that concrete gets a little wet, maybe it's a little less grippy. Do you see that? The decimal got smaller. A smaller decimal means a little less grippy, which probably means less friction. Look down here. If instead of being on concrete, imagine we were trying to walk on some ice. Whoa. The decimal got a lot smaller. It was 0.68, now it's 0.15. Again, smaller decimal means less grippiness. So as you could see, if you're on ice, you don't have as much grip. The bigger the decimal, the more grip, probably the more friction that you have. There's no units here. There's no measurement. These are just decimals. And again, you're not expected to memorize these. On a problem, it would say, oh, the coefficient is 0.68. Or maybe you're asked to calculate it, but you do not have to memorize any of these numbers. So that's the last bit. So we learned what friction is. We saw some examples. Friction sometimes helps us. It sometimes kind of gets in the way. We can also calculate friction, and friction is based on that support force that acts on objects, but also this new thing. This is based on the interaction of material. It's called mu, or the coefficient of friction. This is an equation that you're probably going to get practice with in our science class. Okay? That's all I got. Thanks a lot for watching.